tonight, we're going to explore something that will permanently change how you picture the night sky. We're going to discover the true size of the largest star ever found. And I don't mean a star that's a little bigger than the sun. I mean a star so unimaginably enormous that if you placed it where our sun sits right now, its surface would stretch past the orbit of Saturn. A star so vast that light itself needs over 8 hours just to travel around it once. You've probably heard that stars come in different sizes. But what most people never realize is just how extreme that range actually is. By the end of tonight, you'll understand exactly why some stars grow to such monstrous proportions, and why those stars are ticking time bombs. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something familiar. Our sun. You see it every day. It rises, it crosses the sky, it sets, it warms your skin, it lights your world. From down here on the surface of Earth, the sun looks like a modest glowing disk, about the size of a coin held at arm's length. It seems manageable, approachable even. But the sun is not small. Not by any human standard. The sun has a diameter of about 864,000 miles. That's roughly 1,392,000 kilometers. To put that into perspective, you could line up about 109 Earths across the face of the sun. Not around it, across it. If the sun were hollow, you could fit approximately 1,300,000 Earths inside it. Every continent, every ocean, every mountain range, every city you've ever visited or even heard of, all of human civilization from the first campfire to the latest skyscraper, it all exists on a planet that could fit inside the sun over 1 million times. The sun's mass is about 332,900 times the mass of Earth. It contains 99.86% of all the mass in the entire solar system. Everything else combined, Jupiter, Saturn, all the rocky planets, every moon, every asteroid, every comet, every grain of dust drifting between the planets, all of it together makes up just 0.14%. The sun is the solar system. Everything else is just debris caught in its gravitational grip. The sun is also extraordinarily powerful. Every single second, the sun converts roughly 600 million tons of hydrogen into helium through nuclear fusion in its core. This process releases energy on a scale that's almost impossible to describe. The sun produces more energy in 1 second than all of human civilization has generated in its entire history. The core temperature is about 27 million degrees Fahrenheit. The pressure at the center is about 260 billion times the atmospheric pressure at Earth's surface. These are conditions so extreme that atoms are stripped of their electrons, and hydrogen nuclei are forced together despite their natural electromagnetic repulsion, fusing into helium and releasing energy in the process. This is what defines a star. A star is not just a ball of hot gas. A star is a massive sphere of plasma held together by its own gravity, with conditions at its center so extreme that nuclear fusion occurs. Fusion is the engine. Gravity is the container. And the balance between these two forces, the outward push of radiation and thermal pressure from fusion against the inward pull of gravity, is what determines a star's size, its brightness, its temperature, and ultimately its fate. Now, here's something important that most people don't realize. When we talk about the size of a star, we could mean several different things. Size, mass, and luminosity are three separate properties, and they don't always scale together the way you might expect. A star can be enormous in radius but relatively modest in mass. A star could be incredibly massive but compact and small in diameter. And a star can be blindingly luminous without being particularly large. Understanding this distinction is critical to understanding why some stars grow to such extraordinary dimensions. Mass is the amount of matter in a star. It's measured relative to the Sun. A star with 2 solar masses contains twice as much matter as the Sun. Mass is the most important property of a star because it determines almost everything else about its life. How hot it burns, how long it lives, how it dies. Radius is the physical size, the distance from the center of the star to its surface. This is what we usually mean when we talk about how big a star is. When someone sees a star is 1,000 times larger than the Sun, they typically mean its radius is 1,000 times the Sun's radius. Luminosity is the total amount of energy a star radiates every second. It's a measure of brightness, but not the brightness you see from Earth, which depends on distance. Luminosity is the intrinsic power output, how much energy the star actually produces regardless of how far away it is. For most of a star's life, these three properties are closely related. During the longest and most stable phase of a star's existence, called the main sequence, a star's mass determines its radius and luminosity in a predictable way. More massive stars are larger and more luminous. Less massive stars are smaller and dimmer. This relationship is so reliable that astronomers can estimate a main sequence star's mass just by measuring its luminosity and temperature. The main sequence is where stars spend the vast majority of their lives. It's the phase during which a star is steadily fusing hydrogen into helium in its core. The Sun is a main sequence star right now. It's been on the main sequence for about 4.5 billion years and will remain there for another 5 billion years or so. During this entire time, it won't change dramatically. It will gradually get slightly brighter and slightly larger, but the changes are slow, taking billions of years to become noticeable. On the main sequence, the range of stellar sizes is surprisingly modest compared to what we'll encounter later. The smallest main sequence stars are the red dwarfs. These are stars with masses less than about half the mass of the Sun. Proxima Centauri, the nearest star to our solar system, is a red dwarf with a mass of about 12% of the Sun's mass and a radius of about 15% of the Sun's radius. That means Proxima Centauri is roughly 133,000 miles across. It's much smaller than the Sun, but still enormous by any human standard. It's about 17 times wider than Earth. Red dwarfs are the most common type of star in the galaxy, making up roughly 70% of all stars. But they're so dim that not a single one is visible to the naked eye from Earth. Every star you can see on a clear night is either larger and brighter than the Sun, or is a planet reflecting the Sun's light. Red dwarfs are everywhere, but they're hidden by their own faintness. The smallest known star that still qualifies as a true star, meaning it's massive enough to sustain hydrogen fusion in its core, has a mass of about 8% of the Sun's mass. Below that threshold, the object doesn't have enough gravitational pressure at its center to ignite hydrogen fusion. It becomes a brown dwarf instead, a failed star that glows faintly from the heat of its formation, but never achieves true stellar fusion. The boundary between the smallest star and the largest brown dwarf is remarkably sharp. Just a few percent more or less mass makes the difference between a star that will shine for trillions of years and a dim object that will slowly cool and fade into darkness. On the other end of the main sequence are the massive stars. These are the blue giants and blue supergiants. Stars with masses 10, 20, 50, or even over 100 times the mass of the Sun. These stars are dramatically larger, hotter, and more luminous than the Sun. A star with 20 solar masses might have a main sequence radius of about 8 to 10 times the Sun's radius. A star with 50 solar masses might be 15 to 20 times the Sun's radius while on the main sequence. These are big stars. If you replace the Sun with a main sequence star of 50 solar masses, its surface would extend well past the orbit of Mercury. But even these large main sequence stars are modest compared to what they'll become later. Their main sequence radii are measured in tens of solar radii at most. The most massive stars known have masses around 150 to 200 times the mass of the Sun, though there's some debate about the exact upper limit. A star called R13601, located in the Large Magellanic Cloud, has an estimated mass of about 170 to 230 solar masses, making it one of the most massive stars ever discovered. Even so, its radius on the main sequence is estimated at around 30 to 40 solar radii. That's large, about 25 million miles across. But in the world of stellar sizes, this is still relatively contained. The star is massive, incredibly luminous, blisteringly hot with a surface temperature of about 46,000 degrees Celsius, but physically compact compared to the true giants we'll encounter soon. Here's a key insight about main sequence stars. The more massive a star is, the shorter its life. This seems counterintuitive. You'd think a bigger star with more fuel would last longer. But massive stars burn through their fuel at a vastly disproportionate rate. The rate of fusion doesn't just increase with mass, it increases much faster than mass. A star with 10 times the Sun's mass doesn't live 10 times shorter. It lives roughly 300 to 500 times shorter. The Sun will spend about 10 billion years on the main sequence. A star with 10 solar masses will spend only about 20 million years. A star with 50 solar masses might last only a few million years. And the most massive stars, those rare beasts with over 100 solar masses, might spend less than 2 million years on the main sequence before exhausting their hydrogen fuel. This means the most massive stars in the universe are also the most short-lived. They blaze with extraordinary power but burn out quickly. A star with 100 solar masses will live for perhaps 2 million years total. By comparison, the Sun is 4.5 billion years old and still has billions of years to go. The most massive stars live and die in the time it takes for continents on Earth to shift noticeably. They're cosmic fireworks, brilliant but brief. Now, let's talk about temperature, because temperature tells us something important about a star's color and its physical state. On the main sequence, there's a direct relationship between mass, temperature, and color. The most massive stars are the hottest, with surface temperatures exceeding 30,000 degrees Celsius. These stars appear blue or blue-white. The Sun, a mid-range star, has a surface temperature of about 5,500 degrees Celsius, and appears yellowish white. The smallest red dwarfs have surface temperatures of about 2,500 to 3,500 degrees Celsius and appear reddish-orange. This color-temperature relationship is important because it tells us something crucial about the bigger stars we'll encounter later. The largest stars in the universe are not blue, they're red. They're cool, at least by stellar standards, with surface temperatures of around 3,000 to 3,500 degrees Celsius. This might seem surprising. If bigger means hotter on the main sequence, why are the biggest stars cool? The answer lies in what happens when stars leave the main sequence, when they start to die. And that's where our story takes a dramatic turn. Because here's the thing about the main sequence, it's the stable phase, the calm before the storm. During the main sequence, a star is in equilibrium. The energy produced by fusion in the core pushes outward, perfectly balancing the inward pull of gravity. The star doesn't expand or contract significantly. It just burns steadily, converting hydrogen to helium year after year, century after century, for millions or billions of years depending on its mass. But this equilibrium can't last forever. The hydrogen in the core is finite. It's being consumed constantly, and eventually, inevitably, it runs out. When a star exhausts the hydrogen in its core, the balance that has kept it stable for millions or billions of years is broken. And what happens next depends entirely on how massive the star was to begin with. For low-mass stars like the Sun, the end comes relatively gently, at least at first. For massive stars, the end involves expansion on a scale that is almost beyond comprehension. The star doesn't just get bigger, it inflates to hundreds or even thousands of times its original size. And understanding why this happens, understanding the physical mechanism that drives this extraordinary expansion, is the key to understanding why the largest stars in the universe are as large as they are. So let's set aside the comfortable world of main sequence stars. Let's leave behind the familiar, the stable, the predictable. Because from this point forward, we're entering the realm of stellar extremes. We're going to follow massive stars through their final acts, watching as physics takes over and drives them to sizes that challenge our ability to comprehend. We're going to understand exactly why some stars swell to dimensions that would swallow most of our solar system. And then we're going to meet those stars face to face. Let me put the range of main sequence stars into perspective one more time, because this matters for everything that follows. On the main sequence, the smallest stars are about 10% the size of the Sun. The largest are about 30 to 40 times the size of the Sun. That's a range of roughly 400 to 1. That sounds like a big range, and it is. But it's nothing compared to the range we'll see when we include evolved stars. The largest evolved stars are over 2,000 times the size of the Sun. That's a range from the smallest red dwarf to the largest red supergiant of roughly 20,000 to 1. The main sequence, as broad as it seems, occupies only a small fraction of the total range of stellar sizes. The real extremes happen off the main sequence when stars start to die. And here's something else worth noting. The main sequence isn't just a classification, it's a physical state. A star on the main sequence is in equilibrium. It's stable, it's burning hydrogen in its core at a steady, predictable rate. The moment a star leaves the main sequence, that stability ends. The star enters a period of rapid change, of expansion and contraction, of shifting energy sources and evolving structure. The main sequence is the calm. Everything after it is the storm. And the largest stars in the universe are products of that storm. Think about what this means for the night sky you see above you. Most of the stars visible to the naked eye are main sequence stars or evolved giants. Some are red giants, stars like the Sun that have left the main sequence and expanded to modest proportions. A few are red supergiants, massive stars that have expanded to extraordinary dimensions. Betelgeuse, that bright reddish star in Orion, is one of them. When you look at Betelgeuse, you're looking at a star that is over 700 times the size of the Sun. A star that would engulf Mars if it replaced the Sun. And it's visible as a bright star in the winter sky, looking much like any other star to the casual observer. You'd never guess, just by looking at it, that it's one of the largest objects in the galaxy. But Betelgeuse, as enormous as it is, isn't even in the top 10 for stellar size. There are stars out there that make Betelgeuse look small. Stars so large that they make our entire inner solar system disappear. And understanding how those stars got so large requires understanding what happens inside a star when the hydrogen runs out. That's the physics of stellar evolution, and it's the engine that creates the largest objects in the stellar universe. Let me give you one more sense of scale before we move on. The Sun is about 864,000 miles across. If you could drive a car at highway speeds, say 70 miles per hour, non-stop, it would take you about 514 days to drive from one side of the Sun to the other. That's about a year and 5 months of continuous driving just across our star. And the Sun is a completely ordinary, middle-of-the-road star. It's not particularly large, it's not particularly small, it's average. Now consider this. The largest stars we know of have radii over 2,000 times the Sun's radius. That means their diameter is over 2,000 times wider. If it takes a year and 5 months to drive across the Sun, it would take nearly 3,000 years of continuous driving to cross one of these giant stars. 3,000 years. That's roughly the span of time from the founding of ancient Rome to today. The entire history of Western civilization, from the Roman Republic to the modern era, compressed into a single car ride across a single star. These numbers seem impossible. They seem like exaggerations, but they're not. The physics behind them is well understood, and the stars themselves have been observed and measured. They exist. Right now, in our galaxy and in others, there are stars so enormous that if you could stand on a planet orbiting one of them at a distance comparable to Earth's distance from the Sun, the star would fill your entire sky from horizon to horizon. You wouldn't see a disk in the sky like we see the Sun. You would see nothing but star in every direction you looked. But how does a star get that big? What physical process can take a star that might have been 15 or 20 times the Sun's radius during its main sequence life and inflate it to 2,000 times the Sun's radius? The answer lies in what happens deep inside a star's core when the fuel begins to change, and that's exactly where we're headed next. Before we get there though, let's make sure the foundation is solid, because understanding the larger stars requires understanding gravity, not in the casual, everyday sense of things falling down, but in the deep, relentless, all-consuming sense that governs every moment of the star's existence. Gravity is trying to destroy every star. Right now, at this very moment, The sun's gravity is trying to crush it. Every atom in the sun is being pulled toward the center by the combined gravitational attraction of all the other atoms. The mass is staggering. 2 nonillion kilograms. That's a 2 followed by 30 zeros. All of that mass pulling inward. If fusion stopped in the sun's core right now, if the energy source just switched off, the sun would begin to collapse under its own weight almost immediately. The outward pressure that keeps it inflated would fade, and gravity, patient and unrelenting, would win. But fusion hasn't stopped. Not yet. And as long as fusion continues, it generates the energy that creates the pressure that holds the star up against gravity. This is the fundamental balance of stellar physics. It's called hydrostatic equilibrium. Gravity pulls inward, pressure pushes outward. When these two forces are perfectly balanced, the star is stable. It neither expands nor contracts. It just exists, burning steadily, maintaining its size. The main sequence. This balance is beautifully self-regulating. If the core generates slightly too much energy, the extra pressure causes the star to expand slightly. This expansion cools the core, which slows fusion, which reduces pressure, which causes the star to contract back to its equilibrium size. Conversely, if fusion slows down for any reason, the star contracts slightly under gravity's pull. This contraction heats the core, which speeds up fusion, which increases pressure, which pushes the star back outward. It's a thermostat. A natural feedback loop that keeps the star stable for millions or billions of years. This self-regulation is why main sequence stars are so predictable. Their sizes, temperatures, and luminosities are all determined by their mass, and they stay remarkably constant throughout the main sequence phase. A star with 10 solar masses will have roughly the same radius today as it did 10 million years ago, because the thermostat keeps it in check. But here's the critical point. This thermostat only works as long as the fuel in the core lasts. The moment the core runs out of hydrogen, the thermostat breaks. And when it breaks, gravity, which has been patiently waiting for billions of years, finally gets its chance. What happens next is one of the most dramatic transformations in all of nature. A stable, well-behaved star begins to change in ways that would be unrecognizable. Its core contracts, its envelope expands, its color shifts, its brightness changes. And for the most massive stars, this transformation is so extreme that the star can swell to a size that dwarfs anything it was during the main sequence. The story of the largest stars is really the story of gravity's patience. For millions of years, fusion holds gravity at bay. But fusion is finite. Gravity is forever. And when the fuel runs out, gravity wins. What it does with that victory is what creates the most extraordinary objects in the stellar universe. To understand what happens when a star's core exhausts its hydrogen, you need to picture the interior of a star. It's not uniform. It's layered. At the center is the core, the densest, hottest region where fusion occurs. Surrounding the core are successive layers of progressively less dense and cooler material, extending all the way out to the surface, which astronomers call the photosphere. This is the part of the star we actually see, the glowing surface from which light escapes into space. During the main sequence, fusion occurs only in the core. The rest of the star is essentially just an envelope of gas sitting on top, held up by the energy flowing outward from the core below. The envelope doesn't fuse anything. It's just there, responding to whatever the core does. If the core puts out more energy, the envelope puffs up slightly. If the core puts out less, the envelope settles down. The envelope follows the core's lead. Now, in a star like the Sun, the core takes up roughly the inner 10 to 20% of the star's radius, but it contains a significant fraction of the total mass because it's so dense. The conditions in the core are extreme. Temperatures of tens of millions of degrees, pressures billions of times Earth's atmospheric pressure, density many times the density of lead. In these conditions, hydrogen nuclei, which are just single protons, move so fast and are packed so tightly that they overcome their electromagnetic repulsion and fuse together into helium nuclei. Each fusion reaction converts a tiny amount of mass into energy according to Einstein's famous equation. The mass that disappears becomes the energy that lights the star and holds it up against gravity. In higher mass stars, the core is proportionally larger and the conditions are even more extreme. A star with 20 solar masses has a core temperature several times higher than the Sun's. The fusion reactions proceed at a much faster rate, which is why these stars are so much more luminous than the Sun, and why they exhaust their fuel so much more quickly. The key thing to understand is this: fusion in the core is what keeps the star alive. When fusion stops, the story changes completely. And understanding what happens at that moment, the moment the last hydrogen atom in the core is converted to helium, is the key to understanding why some stars grow to sizes that seem physically impossible. Let's follow a massive star through this transition, not a star like the Sun, which will go through a gentler version of these events, but a truly massive star. A star born with perhaps 20 or 25 times the mass of the Sun. A star that blazed through its main sequence life in just 8 to 10 million years, burning hydrogen at a prodigious rate, shining with a luminosity of tens of thousands of suns. A star that, on the main sequence, had a radius of maybe 10 to 12 times the Sun's. Respectable, but nothing compared to what's coming. This star has just exhausted the hydrogen in its core. The core is now almost entirely helium. And helium, at the temperatures and pressures present in the core at this moment, does not fuse. Helium fusion requires significantly higher temperatures than hydrogen fusion, about 100 million degrees Celsius, compared to the roughly 15 to 20 million degrees needed for hydrogen fusion. The core isn't hot enough yet, so fusion stops in the core, and without fusion, there's no energy source to create the pressure that holds the core up against gravity. Gravity, which has been held at bay for millions of years, immediately begins to reassert itself. The core starts to contract. This is where things get interesting, and this is where the largest stars in the universe begin to take shape. As the core contracts under gravity, it heats up. This is a fundamental property of gas under compression. When you compress gas, it gets hotter. The gravitational energy released by the contraction is converted into thermal energy. The core gets denser and hotter, even though no fusion is occurring within it. The core is essentially falling inward, and the energy of that fall is heating it up. Now, the core isn't the only part of the star affected by this contraction. Remember, the core is surrounded by a vast envelope of hydrogen-rich gas. The layer of gas immediately above the contracting core is being heated by the energy released from the core's contraction. And this layer, which still contains plenty of hydrogen, reaches conditions where hydrogen fusion can ignite. Fusion begins in a shell around the core, burning hydrogen into helium in a thin layer surrounding the inert helium core. This is called hydrogen shell burning, and it changes everything. Shell burning is far more intense than the core fusion that preceded it. The shell is being squeezed from both sides, compressed between the contracting core below and the weight of the envelope above. The fusion reactions in the shell proceed at a much higher rate than they did when hydrogen was burning in the core. The shell pours enormous amounts of energy into the envelope above it, and the envelope responds. It expands dramatically. The excess energy from shell burning pushes the outer layers outward. The star begins to swell, but as the outer layers expand, they cool. The surface temperature drops. The star, which might have been a hot blue or white star on the main sequence, starts to turn orange, then red. Its radius increases by factors of 10, then 100, then more. The star is becoming a giant. And if it's massive enough, it becomes a supergiant. This is the mechanism. This is the engine that creates the largest stars in the universe. It's not that these stars are born large. They're born as relatively compact main sequence stars. They become large because of what happens when their core fuel runs out. The contraction of the core triggers shell burning, and shell burning inflates the envelope to extraordinary dimensions. The physics behind this expansion involves a principle sometimes called the mirror principle in stellar astrophysics. When the core contracts, the envelope expands. When the core expands, the envelope contracts. The core and the envelope behave like opposite ends of a seesaw. This happens because the total gravitational energy of the star must be distributed between the core and the envelope. As the core releases gravitational energy by contracting, that energy flows into the envelope, causing it to expand. But why does the expansion go so far? Why doesn't the star just puff up a little bit and settle into a new equilibrium? The answer has to do with the nature of shell burning and how the envelope transports energy. In a massive star, the envelope becomes so extended and so cool at its outer edge that it becomes convective. Convection is the process where hot gas rises and cool gas sinks, carrying energy upward through bulk motion rather than through radiation. Think of a pot of boiling water. The hot water at the bottom rises to the surface, releases its heat, cools, and sinks back down. The same thing happens in the outer layers of a giant star. Convection is very efficient at transporting energy. As the shell burning intensifies and pours more energy into the envelope, convection carries that energy outward, and the envelope keeps expanding. The more it expands, the cooler the outer layers become, and the more opaque they get. Opacity is a measure of how difficult it is for radiation to pass through a material. Cool gas is generally more opaque than hot gas because cool atoms can absorb more wavelengths of light. Higher opacity means radiation has a harder time escaping, which traps more energy, which drives more convection, which drives more expansion. This creates a kind of feedback loop. Shell burning heats the envelope expands and cools. The cooled envelope becomes more opaque. Higher opacity traps more energy. Trapped energy drives more expansion. And the star keeps growing and growing, limited only by how much energy the shell burning can provide and how much mass is in the envelope. For a star like the Sun, this process will eventually produce a red giant with a radius of about 100 to 200 times the Sun's current radius. When the Sun reaches this stage, about 5 billion years from now, its surface will extend roughly to the orbit of Earth. Mercury and Venus will be engulfed. Earth will either be consumed or will orbit just barely outside the expanded Sun's surface, scorched and lifeless either way. But for a star with 20 or 25 solar masses, the expansion is far more dramatic. These stars have much larger envelopes, they have more powerful shell burning, and their cores go through multiple stages of nuclear burning, each stage contracting the core further and releasing more energy into the envelope. The result is a red supergiant, a star with a radius of hundreds or even over 1,000 times the Sun's radius, a star so vast that it defies easy description. And the expansion doesn't stop with just one round of shell burning. In a massive star, the core eventually gets hot enough to ignite helium fusion. Helium nuclei begin fusing into carbon and oxygen at temperatures around 100 to 200 million degrees. This helium core burning provides a new energy source, stabilizing the core for a time. But helium burning doesn't last nearly as long as hydrogen burning. For a 20 solar mass star, core helium burning might last only about 1 million years, compared to the roughly 8 million years of core hydrogen burning. When the helium in the core is exhausted, the same process repeats. The core contracts again. A helium-burning shell ignites around the carbon-oxygen core, and now there's a hydrogen-burning shell above that. The star develops an onion-like structure, with successive shells of different nuclear burning surrounding an ever denser, ever hotter core. Each round of shell ignition pumps more energy into the envelope. Each round drives more expansion. For the most massive stars, those above roughly 8 to 10 solar masses, this process continues through successively heavier elements. Carbon fuses into neon and magnesium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. Each stage burns faster than the last. Carbon burning might last a few thousand years. Neon burning might last a few years. Oxygen burning might last a few months. Silicon burning, the final stage, lasts roughly 1 day. 1 day. A star that spent millions of years on the main sequence, that took hundreds of thousands of years to go through its giant phases, burns through its silicon fuel in a single day. The acceleration is breathtaking. The star is racing toward its end, and throughout all these stages, the envelope has been expanding. With each successive round of core contraction and shell ignition, more energy has been dumped into the outer layers. The star has grown from a compact main sequence object to a bloated supergiant. Its core is now a tiny, incredibly dense ball of iron and nickel, perhaps the size of Earth, but containing more mass than the Sun. And surrounding that core is an enormous, diffuse envelope of gas extending outward for hundreds of millions or even billions of miles. The star is now a red supergiant. And it's in this state, this bloated, extended, dying state, that stars reach their maximum physical size. The largest stars ever discovered are all in this state. They're not large because they were born large. They're large because the physics of stellar death has inflated their outer layers to extraordinary dimensions. Let me give you a concrete example. Betelgeuse. You've probably heard of it. It's one of the most famous stars in the night sky. The bright reddish star that marks the shoulder of the constellation Orion. Betelgeuse is a red supergiant. It started its life as a hot, luminous main sequence star with perhaps 15 to 20 times the mass of the Sun. On the main sequence, it would have been a brilliant blue star with a radius of maybe 7 to 10 times the Sun's, but it's long since left the main sequence. Its core has exhausted its hydrogen and is now burning helium or possibly heavier elements. Betelgeuse's current radius is estimated at roughly 764 times the radius of the Sun. Some measurements put it higher, some lower, because Betelgeuse actually pulsates. It swells and contracts over periods of months to years, changing its radius by 10 or 20%. But even at its minimum size, Betelgeuse is enormous. If you place Betelgeuse where the Sun is, its surface would extend past the orbit of Mars. Earth, at its distance of 93 million miles from the Sun, would be deep inside the star. Mars, at its average distance of about 142 million miles, would also be inside or just barely at the surface, depending on which measurement of Betelgeuse's radius you use. Betelgeuse is roughly 446 million times the volume of the Sun. That's a staggering number. But here's the thing. Betelgeuse isn't even close to being the largest star we know of. It's large, yes. It's famous, yes. It's a classic example of a red supergiant. But there are stars out there that make Betelgeuse look modest. Stars with radii not 700 times the Sun's, but 1500, 1800, or even over 2000 times the Sun's. These are the true giants, the Leviathans, and they're the stars we're going to meet next. Antares is another well-known red supergiant, the bright reddish star at the heart of the constellation Scorpius. Its name literally means rival of Mars in Greek, because its red colour is similar to the planet Mars. Antares has a mass of roughly 12 to 15 times the Sun's mass, and a radius of approximately 680 times the Sun's radius. It's comparable to Betelgeuse in many ways, a massive star nearing the end of its life, its envelope inflate to enormous proportions by the same shell burning physics we've been discussing. If you placed Antares where the Sun is, its surface would extend past the orbit of Mars, just like Betelgeuse. Antares is also surrounded by a diffuse nebula of gas that has been shedding from its outer layers. This gas loss is important, and we'll talk more about it later, because it's one of the factors that limits how large a star can grow. Both Betelgeuse and Antares give us a window into the physics of stellar expansion. They show us what happens when massive stars leave the main sequence and begin their journey toward death. They show us the shell burning, the envelope inflation, the dramatic increase in size, and they hint at something even more extreme. Because if a star with 15 or 20 solar masses can expand to 700 times the Sun's radius, what happens to a star with 25 or 30 solar masses? What about 40 solar masses? The answer is that these more massive stars expand even more, much more, and the largest of them reach sizes so extraordinary that they stretch the limits of what seems physically possible. Stars so vast that they would engulf not just the inner planets, not just Mars, not just the asteroid belt, but Jupiter, Saturn, and in some cases even the orbit of Saturn itself. These are the stars we're going to explore now. The most extreme red supergiants ever discovered. Stars whose dimensions are so large that describing them requires comparisons to the entire solar system. Stars that represent the absolute pinnacle of stellar size. And every single one of them is a dying star. A star in its final throes, its envelope bloated beyond recognition, its core racing toward collapse. The largest stars in the universe are also among the most fragile, and their existence is fleeting on a cosmic timescale, a few 100,000 years, maybe 1,000,000 at most, and then they're gone. Let's meet them. VY Canis Majoris was, for many years, considered one of the largest stars ever discovered. Located about 3,900 light-years from Earth, in the constellation Canis Major, it's a red hypergiant, a term used for the most extreme red supergiants. VY Canis Majoris has an estimated radius of roughly 1,420 times the radius of the Sun. Think about that number for a moment. 1,420 solar radii. The Sun's radius is about 432,000 miles. Multiply that by 1,420 and you get a radius of approximately 613 million miles. If you placed VY Canis Majoris at the center of our solar system, where the Sun currently sits, its surface would extend past the orbit of Jupiter. Jupiter orbits the Sun at an average distance of about 484 million miles. VY Canis Majoris, with a radius of 613 million miles, would extend well past Jupiter and reach about 2/3 of the way from Jupiter's orbit to Saturn's. Every inner planet, the asteroid belt, and the gas giant Jupiter would all be inside this single star. The volume of VY Canis Majoris is approximately 2.87 billion times the volume of the Sun. You could fit nearly 3 billion suns inside it. Or, to put it in terms of Earth, you could fit approximately 3.7 quadrillion Earths inside VY Canis Majoris. 3.7 quadrillion. That number is so large, it's almost meaningless. If every person on Earth represented one Earth-sized planet, you'd need roughly 500,000 times the current world population to fill VY Canis Majoris. But despite its enormous size, VY Canis Majoris is not particularly massive. Its mass is estimated at roughly 17 to 25 times the mass of the Sun. This might seem like a contradiction. How can a star that's over 1,400 times the Sun's radius have only 20 or so times the Sun's mass? The answer is that VY Canis Majoris is extraordinarily diffuse. Its outer layers are so thin, so spread out that they barely qualify as a gas by Earth standards. The density at the surface of VY Canis Majoris is millions of times lower than the density of air at sea level on Earth. It's essentially a vacuum by any normal standard. If you could somehow stand at the edge of VY Canis Majoris, you wouldn't feel like you were inside a star. You'd feel like you were floating in nearly empty space, with just a faint reddish glow surrounding you. This extreme diffuseness is characteristic of all the largest red supergiants. Their outer envelopes are so extended and so tenuous that defining where the star ends and empty space begins becomes genuinely difficult. There isn't a sharp surface like the surface of Earth. The gas just gradually gets thinner, and thinner as you move outward until it blends imperceptibly into the interstellar medium. Astronomers usually define the star's radius as the point where the gas becomes opaque enough that photons can't escape directly, a layer called the photosphere. But for these extreme supergiants, even this definition becomes fuzzy because the transition from opaque to transparent is very gradual. VY Canis Majoris is also losing mass at an extraordinary rate. Its stellar wind, the stream of gas flowing outward from its surface, carries away roughly 1/10,000th to 1,000th of a solar mass every year. That might not sound like much, but over hundreds of thousands of years, it adds up. VY Canis Majoris is literally evaporating, shedding its outer layers into space, creating an enormous nebula of gas and dust around itself. Observations with the Hubble Space Telescope have revealed complex structures in this nebula, arcs and knots and filaments of ejected material that trace the star's violent history of mass loss. This mass loss is important because it tells us that these extreme supergiants are unstable. They're not calmly sitting in space maintaining their enormous size. They're actively falling apart. Their outer layers are so loosely bound by gravity that they're being blown away by the star's own radiation and convective motions. VY Canis Majoris is a star that is simultaneously as large as it can possibly be, and in the process of becoming smaller as it sheds its outer layers into space. Now, let's move on to another contender, UY Scuti. This star has been one of the most frequently cited candidates for the largest known star, though its ranking has shifted as measurements have been refined. UY Scuti is located about 5,200 light-years from Earth in the constellation Scutum. It's a red supergiant with an estimated radius of approximately 1,708 times the radius of the Sun, though some recent analyses have suggested a somewhat smaller value around 750 to 1,000 solar radii. Let me use the often cited figure to illustrate the scale while acknowledging the uncertainty. At 1,708 solar radii, UY Scuti's radius would be approximately 738 million miles. Placed at the center of our solar system, its surface would extend past the orbit of Jupiter and approach or even reach the orbit of Saturn, which orbits at an average distance of about 887 million miles from the Sun. Whether UY Scuti's surface would actually reach Saturn's orbit depends on which measurement you trust, but even the more conservative estimates put it well past Jupiter. The volume implied by a radius of 1,708 solar radii is roughly 5 billion times the volume of the Sun. 5 billion suns. And at this scale, you could fit approximately 6.5 quadrillion Earth-sized planets inside UY Scuti. The number is so enormous that it has no intuitive meaning for a human mind. It's just large. Unimaginably large. UY Scuti has a mass of roughly 7 to 10 times the mass of the Sun. This is actually less massive than VY Canis Majoris, and yet it's possibly larger in radius. This again illustrates the disconnect between mass and size in the world of red supergiants. These stars are not large because they contain a lot of mass. They're large because their envelopes have been inflated to extreme dimensions by the physics of shell burning. The mass is concentrated in the tiny, dense core. The enormous visible star is mostly just an incredibly thin, diffuse shell of gas. The mass of UY Scuti has actually been one of the sources of uncertainty in its size estimate. If the star is less massive than previously thought, then its luminosity is probably lower, which in turn affects the radius estimate. Stellar radii for distant stars are not measured directly like you might measure the width of a table. They're inferred from a combination of the star's luminosity and its surface temperature, using a fundamental relationship in physics called the Stefan-Boltzmann law. If either the luminosity or the temperature estimate is wrong, the radius estimate changes. This brings us to an important point about how astronomers measure the sizes of these extreme stars. For nearby stars, astronomers can sometimes directly measure the angular diameter, the apparent size of the star on the sky, using a technique called interferometry. This involves combining light from multiple telescopes to achieve extremely high angular resolution. Betelgeuse, for example, is close enough and large enough that its disk has been resolved by interferometric observations. We can actually see that it's not a point of light, but a disk, and we can measure the size of that disk. But for more distant stars like UY Scuti and VY Canis Majoris, direct angular measurements are more difficult. The stars are farther away, so they appear smaller on the sky. Interferometric measurements become harder and more uncertain. In many cases, astronomers rely on indirect methods. They measure the star's brightness, correct for distance using parallax or other distance indicators, determine the luminosity, estimate the surface temperature from the star's color and spectral features, and then use the Stephan-Boltzmann law to calculate the radius. The Stephan-Boltzmann law says that a star's luminosity is proportional to the square of its radius times the fourth power of its surface temperature. If you know the luminosity and the temperature, you can solve for the radius. But there are sources of error at every step. The distance might be uncertain. The brightness might be affected by dust between us and the star. The temperature estimate depends on spectral analysis that can be complicated for cool, extended supergiants with complex atmospheres. All of these uncertainties compound, making radius estimates for the larger stars inherently imprecise. This is why the ranking of the largest known stars shifts over time. A new measurement might revise a star's distance, which changes its luminosity estimate, which changes its radius estimate. A star that was thought to be the largest one year might be demoted the next, when better data becomes available. The science is ongoing, and the numbers are constantly being refined. With that caveat in mind, let's talk about the star that currently holds the strongest claim to the title of the largest known star in the universe, Stephenson 2-18. Stephenson 2-18 is a red supergiant located in the Stephenson 2 open cluster, which sits about 19,000 light-years from Earth, near the dense star fields toward the center of our galaxy. Its estimated radius is approximately 2,150 times the radius of the Sun. 2,150 solar radii. Let that number sink in for a moment. The Sun's radius is about 432,000 miles. Multiply that by 2,150 and you get a radius of approximately 929 million miles. 929 million miles. That's a radius so large that if Stephenson 2-18 replaced the Sun at the center of our solar system, its surface would extend past the orbit of Saturn. Saturn orbits at an average distance of about 887 million miles from the Sun. Stephenson 2-18, with its radius of 929 million miles, would extend roughly 40 million miles beyond Saturn's orbit. Saturn, its famous rings, and everything inward, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, all of it would be inside this single star. Let me try to help you picture this. You're standing on Earth. The Sun is 93 million miles away. It looks like a small bright disk in the sky. Now, imagine the Sun starts growing. It expands past Mercury, past Venus, past you, engulfing Earth entirely. You're now inside the star. The sun keeps expanding. Past Mars, past the asteroid belt, past Jupiter, the largest planet in our solar system, past Saturn with its magnificent rings. The surface of Stephenson 2-18 would finally stop somewhere beyond Saturn's orbit, roughly 930 million miles from where the sun used to be. Everything you've ever known, every planet humans have ever observed through a telescope, every place our spacecraft have ever visited except for the most distant probes heading toward Uranus and Neptune, all of it would be inside one star. The volume of Stephenson 2-18 is approximately 10 billion times the volume of the sun. 10 billion. You could fit 10 billion suns inside it, or roughly 13 quadrillion Earths. The star is so large that light, traveling at 186,000 miles per second, would need nearly 3 hours just to travel from one side of this star to the other. Light crosses the sun in about 4.5 seconds. It crosses Stephenson 2-18 in close to 3 hours. A beam of light could cross the entire distance from the Earth to the Moon in about 1.3 seconds. That same beam would need almost 3 hours to cross Stephenson 2-18. And if that light wanted to travel all the way around the star's circumference, it would take over 8.5 hours. Despite this enormous size, Stephenson 2-18 has a mass estimated at roughly 12 to 40 times the mass of the Sun. The uncertainty in the mass is large, partly because the star is very far away, and partly because mass estimates for red supergiants are inherently difficult. But even at the high end of the estimate, 40 solar masses, the star's mass is modest relative to its size. The average density of Stephenson 2-18 is roughly 1/millionth the density of air at sea level. It's one of the most tenuous objects you could call a star. A hot air balloon on Earth is denser than the outer layers of this star. A laboratory vacuum on Earth contains more matter per cubic centimeter than the outer envelope of Stephenson 2-18. The surface temperature of Stephenson 2-18 is estimated at about 3,200 Kelvin, roughly 3,000 degrees Celsius. That's cool for a star. For comparison, the sun's surface is about 5,800 Kelvin. This low surface temperature is what gives Stephenson 2-18 its deep red color. It's a consequence of the extreme expansion. As the envelope expanded, it cooled. The more it expanded, the cooler it got. And the cooler it got, the redder it appeared. This is why all the larger stars are red. Not because red stars are born large, but because the expansion that makes them large also makes them cool. And cool stars appear red. Now, there are other stars that deserve mention alongside these giants. WOHG 64 is a red supergiant in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years from Earth. Older estimates placed its radius at over 1,500 solar radii, but recent interferometric observations in 2024 using the Very Large Telescope found a revised radius of roughly 770 times the Sun's radius. Even at this smaller size, it's still enormous. If placed at the center of our solar system, its surface would extend past the orbit of Mars and reach roughly halfway to Jupiter. WOHG 64 remains notable for being one of the most luminous red supergiants known, shining with a luminosity of roughly 300,000 times the Sun's luminosity. It is also notable because it sits outside the Milky Way. in a completely different galaxy, reminding us that these giant stars exist throughout the universe, not just in our own neighborhood. There's also Westerlund 1-26, a red supergiant in the Westerlund, one-star cluster about 12,000 to 16,000 light-years from Earth. Its estimated radius is roughly 1,500 to 2,000 solar radii, putting it in the same class as the other extreme supergiants we've discussed. Westerlund 1 is one of the most massive young star clusters in the Milky Way, containing many extremely massive stars. Westerlund 1-26 is the red supergiant member of this cluster, a star that was once among the hottest and most luminous members, but has now evolved to the cool, red, enormously expanded phase of its life. And there's Mu Cephei, sometimes called Herschel's garnet star because of its deep red color, with an estimated radius of roughly 1,420 solar radii. This star was noticed for its striking reddish hue by the astronomer William Herschel, who described its color as garnet. It's one of the most luminous stars in the Milky Way, shining with a luminosity of roughly 350,000 times the Sun's. Like all the other extreme red supergiants, it's losing mass at a significant rate, shedding its outer layers into space and slowly revealing the hot, dense core hidden beneath. Notice something about all these stars. They're all red supergiants. Every single contender for the largest known star is a red supergiant. This isn't a coincidence. It's a direct consequence of the physics we discussed earlier. The only mechanism that produces stars this large is the envelope expansion that occurs during the late stages of massive star evolution. Main sequence stars, no matter how massive, simply don't get this big. Blue giants and blue supergiants are large by main sequence standards, but they're dwarfed by red supergiants. The extreme sizes are exclusively a product of stellar death. Let me try one more comparison to drive home the scale. If you could somehow shrink the sun down to the size of a basketball, roughly 9.5 inches in diameter, then Stephenson 2-18 at the same scale would be a sphere roughly 1,700 feet across. That's taller than any skyscraper ever built. Taller than the Willis Tower and the Empire State Building stacked on top of each other. A basketball next to a structure taller than any building on Earth. That's the difference in size between our sun and the largest known star, or try this one. The International Space Station orbits Earth at about 250 miles above the surface. Earth's diameter is about 7,926 miles. If the Sun were scaled to the size of Earth, Stephenson 2-18 would be a sphere roughly 17 million miles across, over 70 times the distance from Earth to the Moon. You'd replace the modest sphere of Earth with something so large that the Moon, our nearest celestial neighbor, would be well inside it. These comparisons help, but they also fail, because at some point the numbers become so large that no analogy captures the reality. The only honest thing to say is that these stars are large beyond the capacity of the human mind to truly visualize. We can do the math, we can write down the numbers, we can compare and contrast, but we can't truly picture what it would be like to see a star that fills the volume from the Sun to Saturn. Our brains aren't built for that. We evolved to understand distances and sizes relevant to survival on the African savanna, not the interior structure of stellar giants separated from us by thousands of light years. But let me try one more approach. Let's think about what it would actually be like if you could somehow witness one of these stars up close. Imagine you're in a spacecraft approaching Stephenson 2-18 from a great distance. At first, it would look like any other red star, a point of reddish light against the darkness. As you got closer over a period of weeks or months, depending on your speed, the star would begin to resolve into a disk. But unlike approaching the sun, which is a brilliant, sharply defined disk of light, Stephenson 2-18 would appear as a diffuse, reddish glow. The boundary of the star wouldn't be crisp, it would fade gradually, the reddish light getting dimmer and more transparent toward the edges, blending imperceptibly into the surrounding space. As you got closer still, the star would fill more and more of your field of view. If you approach to a distance comparable to Earth's distance from the Sun, roughly 93 million miles, you would be deep inside the star. But you might not even realize it at first. The gas at that distance from the core would be extraordinarily thin, far less dense than any vacuum humans have ever created in a laboratory. You'd be surrounded by a faint reddish glow, like being inside a vast, warm, dimly lit fog. The temperature would be a few thousand degrees, far too hot for your spacecraft to survive without protection. But the material around you would be so thin that it would barely exert any pressure. If you could somehow look toward the center of the star from this position, you'd see the glow getting brighter and denser in one direction. Toward the center, the gas gets progressively thicker, hotter, and more opaque. At some point, deep inside, you'd encounter layers dense enough and hot enough to block your view entirely. Beyond that barrier of increasingly opaque gas lies the core, where temperatures reach hundreds of millions of degrees and where the last stages of nuclear fusion are racing toward their conclusion. If you looked outward, away from the center, you'd see the glow fading gradually into darkness. Somewhere out there, hundreds of millions of miles away, the gas would become thin enough to be transparent, and you'd be able to see the stars of the surrounding galaxy shining through the tenuous outer atmosphere of this dying giant. The experience would be surreal. You'd be inside a star, surrounded by stellar material, but it would feel like being in nearly empty space with a faint, warm glow. The star would be so large and so diffuse that being inside it wouldn't feel like being inside anything solid or substantial. It would be more like being inside a vast, dim, warm cloud, stretching in every direction for hundreds of millions of miles. Now, imagine looking at this star from the outside, from a distance of, say, twice its radius, so roughly 2 billion miles away. The star would appear as an enormous, deep red sphere filling a significant portion of the sky. Its surface wouldn't be smooth. Red supergiants have enormous convective cells on their surfaces, rising plumes of hot gas hundreds of millions of miles across. These convective cells would appear as bright and dark patches on the stellar surface, slowly churning and changing over periods of months. The star's surface would literally be boiling, like the surface of a pot of thick soup, but on a scale that dwarfs anything in our solar system. You might also see material streaming away from the star, wisps and tendrils of gas being blown off the surface by the stellar wind. In some directions, you might see darker regions where cooler, denser gas has condensed into dust, partially obscuring the star's light. The star would be surrounded by a haze of its own exhaled material, a slowly expanding shroud of gas and dust that marks the ongoing dissolution of the star's outer layers. And if you could somehow compress time, watching centuries pass in minutes, you would see the star pulsating, expanding and contracting rhythmically, like a heartbeat. Each pulsation would change the star's size by millions of miles. Each expansion would launch more material into space. Each contraction would compress the outer layers, heating them briefly before the next expansion. The star would breathe, slow and vast, each breath lasting months or years, each exhalation sending more of itself into the void. This is what the largest stars actually are. Not solid objects, not dense, compact structures. They are vast, tenuous, slowly dissolving clouds of hot gas, held together only loosely by gravity, constantly losing material to their own radiation and convection. They are objects in transition, caught between the forces that made them and the forces that will unmake them. They are, in a very real sense, the most fragile large structures in the universe. A star like Stephenson 2-18 is enormous, but it's also gossamer thin. It's held together by the slimmest of margins. A modest increase in luminosity, a particularly violent pulsation, and it could shed a significant fraction of its remaining envelope in a single event. And yet, despite this fragility, these stars are among the most important objects in the cosmos. Their mass loss enriches the interstellar medium even before the final supernova. The gas and dust they shed during their red supergiant phase contributes to the raw material from which new stars and planets will eventually form. They're giving back to the cosmos even as they're dying, returning processed material to the interstellar medium in a slow, continuous stream that supplements the explosive return of the final supernova. There is something deeply moving about this. These are stars at the very end of their lives. They've spent millions of years fusing hydrogen, helium, carbon, neon, oxygen, and silicon. They've built up layer after layer of heavier elements in their cores, and now, as they approach their final moments, they swell to their maximum size, becoming the largest objects they will ever be, the largest objects physics will permit them to be. They stand at the precipice between existence and oblivion, briefly and magnificently vast, before collapsing into something almost unimaginably small. The journey from birth to death for one of these stars spans perhaps 8 to 12 million years. That's a long time by human standards, but practically nothing by cosmic standards. The universe is 13.8 billion years old. A star that lives for 10 million years exists for less than 1,000th of 1% of the age of the universe. And the red supergiant phase, the phase when the star is at its largest, lasts for only a fraction of that total lifespan. It's the final act, the grand finale, and it's over almost as soon as it begins. Every red supergiant you could see in the night sky, Betelgeuse, Antares, and the others, is in this final act right now. They're performing their last moments on the cosmic stage. Their cores are burning through their remaining fuel at an accelerating pace. Their envelopes are swelling and shedding. They're approaching the moment of iron core collapse and supernova detonation. And when that moment comes, they'll be gone, replaced by a tiny remnant and an expanding cloud of debris. The largest stars in the sky will become invisible, their light replaced by the brief flare of a supernova, and then the slow fade of a supernova remnant dispersing into space. And yet, we can understand the physics. We can explain why these stars are as large as they are. We can trace the causal chain from core hydrogen exhaustion to shell burning to envelope inflation to red supergiant expansion. The explanation is elegant and internally consistent. Gravity, fusion, opacity, convection, each piece of physics contributes to the final result. And the final result is a star that fills a volume larger than the orbit of Saturn. The largest stars are cosmic ephemera, brief, magnificent, and doomed. Brief, magnificent, and doomed. They represent the absolute limit of stellar size, the maximum extent to which a star can inflate before physics intervenes and either tears it apart or collapses it into something entirely different. And understanding those limits, understanding why stars can't grow even larger, is the final piece of our story. There is a fundamental limit to how large a star can grow. Actually, there are several limits, each arising from different aspects of physics, and they work together to constrain the maximum size of a star. Understanding these limits tells us why the largest known stars have radii of about 2,000 solar radii and not 20,000 or 200,000. The first and most important limit is the Eddington luminosity limit. This is named after the British astrophysicist Arthur Eddington, who first described it in the early 20th century. The Eddington limit is the maximum luminosity a star can have before radiation pressure overwhelms gravity. Here's how it works. Light exerts pressure. When photons interact with matter, they push on it. This radiation pressure is normally tiny compared to gravity. You don't feel the pressure of sunlight on your skin because it's incredibly weak compared to Earth's gravity. But in a star, the luminosity can be so enormous that radiation pressure becomes a significant force. If a star's luminosity gets high enough, the radiation pressure on the outer layers exceeds the gravitational force, holding those layers in place. At that point, the star literally blows itself apart. The outer layers are pushed away by the star's own light, faster than gravity can hold them down. The Eddington limit depends on the star's mass. More massive stars can support higher luminosities before radiation pressure overwhelms gravity. For a star with 50 solar masses, the Eddington luminosity is roughly 1,600,000 times the Sun's luminosity. For a star with 100 solar masses, it's roughly proportionally higher. Red supergiants approach the Eddington limit as they expand and become more luminous. When a massive star inflates to become a red supergiant, its luminosity increases dramatically. If the luminosity gets too high, radiation pressure starts stripping away the outer layers. This creates a natural cap on how luminous and ultimately how large a red supergiant can be. A star that tries to expand beyond the limit set by its mass will simply lose its outer layers to radiation-driven winds. The star can't grow larger because any additional expansion would be immediately reversed by mass loss. But the Eddington limit, as originally formulated, applies to the luminosity averaged over the entire star. In practice, the situation is more complicated for red supergiants because their outer envelopes are convective. In convective regions, the energy transport isn't just through radiation, it's through bulk motion of gas. Hot gas rises, carrying energy upward, and cool gas sinks. This means the local conditions can temporarily exceed the Eddington limit in some regions, even if the average luminosity is below it. A particularly strong convective upwelling can push material outward faster than gravity can pull it back. This leads to localized mass ejections, blobs of gas, launched from the stellar surface that escape into space. We see exactly this kind of behavior in the real universe. The complex nebula surrounding VY Canis Majoris, which we discussed earlier, shows evidence not of smooth, steady outflow, but of repeated violent ejections. Clumps and arcs of material that were launched from the stellar surface at different times, in different directions, at different speeds. The star is essentially boiling, with its convective outer layers occasionally burping out clumps of material that have been pushed past the escape velocity by convective energy. The second limit comes from mass loss itself. Red supergiants lose mass at phenomenal rates. The most extreme red supergiants shed mass at rates of roughly 1/10,000th to 1,000th of a solar mass every year. At 1,000th of a solar mass per year, a star would lose an entire sun's worth of material in just 1,000 years. Over the hundreds of thousands of years that a star might spend as a red supergiant, this adds up to a substantial fraction of the star's total mass. As the star loses mass, its gravity weakens. With weaker gravity, the star can't hold as much of its envelope. Mass loss therefore sets a limit on the star's maximum size. A star that tries to maintain an enormous envelope while continuously shedding mass will eventually lose too much of that envelope to sustain its size. The envelope shrinks as mass is lost, even as shell burning tries to inflate it. The stellar wind from a red supergiant isn't a gentle breeze, it's a torrent. The gas leaving the surface of a star like VY Canis Majoris flows outward at speeds of roughly 20 to 40 kilometers per second. It carries not just gas, but also dust, tiny particles of solid material that condense in the cooling outflow. This dust can be observed at infrared wavelengths, and it creates the spectacular nebulae we see surrounding many red supergiants. These nebulae are the visible evidence of the star's ongoing destruction, material that used to be part of the star and is now drifting through interstellar space, never to return. The dust plays an important role in driving the wind. As material flows away from the star and cools, solid grains condense out of the gas. These grains are very effective at absorbing and scattering the star's radiation. When a photon from the star hits a dust grain, it gives the grain a little kick. Enough kicks, and the grain is accelerated outward. The gas is dragged along with the dust through collisions between gas molecules and dust grains. So the mass loss from red supergiants is partly a self-reinforcing process. The star's radiation creates dust. The dust absorbs the radiation and is pushed outward. The outward moving dust drags gas with it. This dust-driven wind is a major contributor to mass loss in red supergiants, and it's one of the reasons why these stars have such prodigious mass loss rates. The third limit involves pulsational instability. Red supergiants don't sit quietly at a fixed size. They pulsate. Their outer layers expand and contract in cycles lasting months to years. Betelgeuse, for example, has multiple pulsation periods, the most prominent being roughly about 400 days and another of roughly 2,100 days. During these pulsations, the star's radius can change by 10 to 20% or more. These pulsations are driven by the interplay of opacity and temperature in the outer layers. As a layer of gas contracts, it heats up. As it heats up, its opacity changes. If the opacity increases with temperature, the layer traps more radiation, builds up more pressure, and bounces outward. As it expands, it cools, its opacity drops, radiation escapes, pressure drops, and the layer falls back inward. This cycle repeats, driving the star into rhythmic pulsation. The mechanism is similar to what drives pulsations in other types of variable stars, like Cepheid variables, but in red supergiants, the pulsations occur on longer timescales and involve much larger amplitudes because the outer envelope is so extended and so loosely bound. For the most extreme supergiants, these pulsations can become violent enough to eject material from the star. A particularly strong pulsation can launch a shell of gas off the surface at speeds high enough to escape the star's gravity entirely. This mechanism, called pulsation-driven mass loss, supplements the steady stellar wind and accelerates the rate at which the star sheds its envelope. In late 2019 and early 2020, Betelgeuse underwent a dramatic dimming event that made headlines around the world. The star's brightness dropped by roughly a factor of 3 over a period of months, causing some to wonder if it was about to explode. It wasn't. What actually happened was that Betelgeuse ejected a large mass of gas from its surface, probably triggered by an unusually strong convective upwelling. As this gas expanded and cooled, dust condensed within it. The dust cloud, sitting between us and the star, blocked some of the star's light, causing the apparent dimming. This event was essentially a sneeze, a star ejecting a piece of itself into space, and it gave astronomers a front row seat to the kind of mass loss that shapes the final stages of a red supergiant's life. There may also be a limit related to the star's internal structure. As a red supergiant's envelope becomes more and more extended, the outer layers become increasingly weakly bound to the star. At some point, the binding energy of the outermost layers drops to essentially zero. Any small perturbation, a pulsation, a convective upwelling, a slight increase in luminosity can unbind these layers and send them drifting off into space. This means that beyond a certain radius, the star simply can't hold itself together. Its outer boundary becomes fluid, indeterminate, with the material constantly flowing away and being replaced, at least temporarily, by material pushed outward from the shell burning below. Think of it like a fountain. Water rises from the center, reaches some maximum height, and then falls back or flows away. The maximum height of the fountain isn't determined by how much water you have, it's determined by how much pressure you can apply. Similarly, the maximum size of a red supergiant isn't determined by how much gas is in the envelope. It's determined by how much energy the shell burning can provide and how effectively that energy can be transported to the outer layers. Beyond a certain radius, the energy just isn't sufficient to support the material against gravity, and the material drifts away. All of these factors work together to set the maximum size of a star at roughly 2,000 to 2,500 solar radii. Beyond that, the combination of radiation pressure, mass loss, pulsational instability, and gravitational unbinding prevents the star from maintaining a larger envelope. Some material may temporarily extend beyond this radius during a particularly strong pulsation, but it won't stay there. It will either fall back or escape into space. This is why Stephenson 2-18, with its radius of roughly 2,150 solar radii, sits near the theoretical maximum for stellar size. It's not just the largest star we've found. It's close to the largest star that physics allows. There might be a star somewhere that's slightly larger, perhaps with a radius of 2,300 or 2,500 solar radii during a pulsation maximum. But we're unlikely to find a red supergiant with a radius of 5,000 or 10,000 solar radii. The physics simply doesn't permit it. The star would blow itself apart long before reaching that size. It's worth noting that the theoretical limit isn't perfectly sharp. Different models and different assumptions about mass loss rates, convection efficiency, and opacity give slightly different maximum radii. Some models suggest the limit is closer to 2,000 solar radii. Others push it to about 3,000. But all models agree that there is a limit, and it's in the general range of 2,000 to 3,000 solar radii. Stars larger than this are physically impossible under the known laws of physics. This is actually a satisfying result. It means we're not just cataloguing ever larger stars without end. There's a physical ceiling. And the largest stars we've observed are close to that ceiling. We're seeing nature at its extremes, pushing up against the limits imposed by fundamental physics. Now, let's talk about the end. Because these enormous stars don't last. They can't. Everything about their existence is temporary. The shell burning that inflates them is consuming fuel at a staggering rate. The mass loss is stripping away their outer layers. The pulsations are becoming more violent. The core is racing through heavier and heavier elements, each stage shorter than the last. A massive red supergiant is a star on borrowed time. The end comes when the core produces iron. Iron is the end of the line for nuclear fusion. Every element lighter than iron releases energy when its nuclei are fused together. Hydrogen fuses to helium and releases energy. Helium fuses to carbon and releases energy. Carbon fuses to neon, neon to oxygen, oxygen to silicon, and each step releases energy. But iron is different. Fusing iron nuclei doesn't release energy, it requires energy. Iron sits at the bottom of the nuclear binding energy curve. It's the most tightly bound nucleus. Fusing it into heavier elements or splitting it into lighter elements both require energy input rather than providing energy output. When the core of a massive star becomes filled with iron, fusion stops. There's no longer any energy source to support the core against gravity. The core has been getting progressively denser and hotter with each successive stage of nuclear burning, but it's always been supported by the energy from fusion. Now the support vanishes, and now, after millions of years of patient waiting, gravity finally gets its moment. With no energy to hold it up, the core collapses. Not slowly, not gradually, catastrophically. In less than a second, the iron core of a massive star collapses from roughly the size of Earth to a ball roughly 12 miles across. The material freefalls inward at speeds approaching a quarter of the speed of light. Protons and electrons are crushed together to form neutrons. The core becomes a neutron star, an object of almost inconceivable density. The collapse happens so fast that the outer layers of the star don't have time to respond. They're still sitting there, a vast diffuse envelope of hydrogen and helium extending hundreds of millions of miles into space, completely unaware that the core has just vanished from under them. The core, which used to support all those layers through the energy it provided, is simply gone, replaced by a tiny, incredibly dense ball of neutrons that's too small and too compact to hold up the overlying material in the same way. And then the shockwave hits. When the collapsing core reaches neutron star density, it becomes incompressible. The nuclear strong force between the packed neutrons resists further compression. The infalling material bounces. A shock wave forms at the surface of the new neutron star and begins propagating outward through the star. This shock wave is energized by a flood of neutrinos, ghostly subatomic particles produced in enormous quantities during the core collapse. Normally, neutrinos barely interact with matter. They can pass through the entire Earth without hitting a single atom. But the densities in the collapsing core are so extreme that even neutrinos get temporarily trapped, and their energy helps drive the shockwave outward. The details of how the shockwave successfully plows through the entire star and reaches the surface are still an active area of research. Computer simulations have shown that the shockwave sometimes stalls after a few hundred miles, losing energy as it pushes through the dense layers above the core. It's the neutrinos that revive it. About 5% of the neutrino energy is deposited in the material just above the stalled shockwave, heating it, creating convective motions, and ultimately re-energizing the shockwave so it can continue outward. This neutrino-driven mechanism is one of the great insights of modern astrophysics, though many details are still being worked out. The shockwave tears through the star's interior, heating and compressing the material as it goes. As it passes through each layer, it triggers explosive nucleosynthesis, creating heavy elements that weren't produced during the star's normal nuclear burning. Elements heavier than iron, things like gold, platinum, uranium, are produced partly during these explosive final moments, and partly in other extreme events like the collisions of neutron stars. The extreme temperatures and pressures in the shockwave allow nuclear reactions that couldn't occur under any other conditions. When the shockwave reaches the outer layers, those vast, diffuse, gently pulsating layers that make the star such an enormous red supergiant, it blasts them into space at speeds of thousands of kilometers per second. The star explodes. This is a core collapse supernova, one of the most energetic events in the universe. For a brief period, a few weeks to a few months, the supernova can outshine an entire galaxy. A single exploding star producing more light than hundreds of billions of normal stars combined. The energy released is approximately 10 to the 46 joules, a number so large it defies any attempt at human comprehension. If you took all the energy that the sun will produce over its entire 10 billion year lifetime and released it in 10 seconds, you'd still fall short of the energy output of a core collapse supernova. But even the light energy is only a small fraction of the total. About 99% of the energy released in a supernova is carried away by neutrinos. The visible light, as spectacular as it is, represents only about 1% of the total energy budget. The neutrinos stream outward in all directions at nearly the speed of light, carrying the energy of the collapse with them. Most of them will never interact with anything. They'll travel through space forever, ghostly messengers from a dead star. The explosion scatters the star's outer layers across space, enriching the interstellar medium with heavy elements. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements that were forged in the star's interior during its lifetime are now flung into the cosmos at thousands of kilometers per second. These elements mix with existing clouds of gas and dust, and over millions of years, Those enriched clouds collapse under gravity to form new stars and new planetary systems. This is the cosmic legacy of the largest stars. They live fast, they burn brightly, they grow to extraordinary sizes, and then they explode, seeding the universe with the very elements that make rocky planets and life possible. Every atom of carbon in your body was forged in the core of a massive star. Every atom of oxygen you breathe was created by nuclear fusion inside a star that lived and died billions of years ago. The iron in your blood, the calcium in your bones, the silicon in the rocks beneath your feet, all of it came from stars. And not just any stars. Many of these elements were forged in the cores of massive stars. The same kind of stars that swell into red supergiants with radii of hundreds or thousands of solar radii. The same kind of stars that eventually explode as supernovae, scattering their enriched material across light years of space. Stars like Stephenson 2-18. Stars like VY Canis Majoris. Stars like Betelgeuse, which will itself explode as a supernova within the next 100,000 years or so. This brings us to something profound. The largest stars in the universe are the most temporary. They exist for the shortest periods. This brings us to something profound about the nature of these giant stars. They're not permanent features of the cosmos. They're temporary, fleeting. A red supergiant with a radius of 2,000 solar radii exists in that state for perhaps a few 100,000 years, maybe less. In a universe that's 13.8 billion years old, a few 100,000 years is nothing. It's less than a blink. It's a single heartbeat in the life of the cosmos. The stars that hold the title of largest are constantly changing. Stars that were the largest 1 million years ago have long since exploded. Stars that will be the largest 1 million years from now haven't even been born yet, or they're still on the main sequence, compact and blue, waiting for their core hydrogen to run out so they can begin their transformation. The roster of the universe's largest stars is in constant turnover. A revolving door of giant stars that bloom, swell to extraordinary sizes, and then detonate. After the supernova, what's left at the center depends on the mass of the collapsing core. For most massive stars, the remnant is a neutron star, that incredibly dense ball of neutrons roughly 12 miles across but containing 1.5 to 2 times the mass of the Sun. Neutron stars are extraordinary objects in their own right. A teaspoon of neutron star material weighs about 4 billion tons. They spin rapidly, sometimes hundreds of times per second, and produce beams of radiation that sweep across space like cosmic lighthouses. When these beams happen to cross Earth's line of sight, we detect them as pulsars, rapidly and precisely repeating radio pulses. For the most massive stellar cores, those exceeding roughly 2.5 to 3 times the mass of the Sun after the explosion has stripped away the outer layers, even neutron degeneracy pressure can't stop the collapse. The core continues to fall inward, compressing past the point of no return, and forms a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. The star that once stretched across the solar system, that contained trillions of Earth volumes, has collapsed into a singularity of essentially zero size and infinite density, surrounded by an event horizon perhaps only a few miles across. The contrast is staggering. A star that was once 930 million miles in radius, large enough to engulf Saturn, has become a black hole perhaps 10 or 20 miles across. The transformation from the largest possible stellar object to one of the smallest possible stellar remnants happens in less than a second. One moment, the star fills a volume larger than the orbit of Saturn. Less than a second later, all that remains is a point in space, surrounded by an expanding cloud of debris. This is the story of the largest stars. They're born as hot, compact main sequence stars. They spend millions of years steadily fusing hydrogen. They exhaust their fuel, their cores contract, shell burning ignites, their envelopes expand, slowly at first, then more and more dramatically, until they've swollen to radii of hundreds or thousands of times the sun's. They pulsate, they shed mass, they develop onion layer cores burning heavier and heavier elements, and then, when the core finally produces iron, gravity wins its long battle. The core collapses in less than a second. The star explodes, and what's left is either a neutron star or a black hole, surrounded by an expanding nebula of enriched gas that will eventually contribute to the formation of new stars and new worlds. The expanding debris from a supernova is called a supernova remnant. It's a bubble of hot gas expanding outward at thousands of kilometers per second, glowing with the light of ionized elements. Some of the most beautiful objects in the sky are supernova remnants. The Crab Nebula, for instance, is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. At its center sits a pulsar, a rapidly spinning neutron star that emits beams of radiation as it rotates. The pulsar in the Crab Nebula spins about 30 times per second, a remnant of the angular momentum of the star that created it, concentrated into a ball 12 miles across. Over thousands and millions of years, the expanding supernova remnant slows down as it sweeps up the surrounding interstellar medium. It mixes with existing clouds of gas and dust. The heavy elements it carries, the carbon, oxygen, silicon, iron, gold, and all the rest, are incorporated into these clouds. And when these clouds eventually collapse under gravity to form new stars, the heavy elements come along, enriching the next generation of stars and planets. Our own solar system formed from such an enriched cloud about 4.6 billion years ago. The elements heavier than hydrogen and helium in our solar system, everything from the carbon in organic molecules to the iron in Earth's core, were produced by previous generations of massive stars that lived and died before our sun was born. The sun is at least a second generation star, possibly third generation, meaning it formed from material that had already been processed through one or more previous stellar life cycles. You are made of atoms that cycle through stars. The carbon in your muscles, the oxygen in the water that makes up most of your body, the calcium that gives structure to your bones, the iron that makes your blood red, all of it was forged in the interiors of massive stars, possibly stars as large as the ones we've discussed tonight. Those atoms were scattered into space when those stars exploded, drifted through the cosmos for millions of years, collected into a cloud, collapsed into a new star and its planetary system, and eventually, after 4.6 billion years of geological and biological evolution, ended up in you. Carl Sagan famously said that we are star stuff, and it's true, but it's more specific than that. We are supernova stuff. We are the debris of exploded giant stars, reorganized by billions of years of chemistry and biology into conscious beings who can look up at the night sky and understand the story of where we came from. There's something beautiful about that impermanence. These stars exist at the very edge of what physics allows. They're as large as gravity and radiation and nuclear physics permit. They occupy a narrow range of conditions where the envelope can expand to extreme dimensions without being blown away or collapsing. They balance, briefly and precariously, between the forces that create them and the forces that will destroy them. In a way, the largest stars represent nature at its most extreme. They show us what happens when the fundamental forces of the universe push matter to its limits. Gravity pulls inward, radiation pushes outward, nuclear fusion provides the energy, mass loss drains the envelope, pulsations shake the structure, and in the middle of all this, for a few 100,000 years, a star the size of Saturn's orbit exists. It glows with the light of hundreds of thousands of suns. It sheds material into space at rates that would empty a star like the Sun in millennia. And then it collapses and explodes, returning its material to the cosmos to be recycled into new stars, new planets, and perhaps new life. Let me leave you with a final thought about what all this means for us. You exist because of stars like these. The atoms in your body, the oxygen you breathe, the carbon in your DNA, the iron in your blood, all of it was forged inside massive stars during their lifetimes and scattered into space when they exploded. You are, quite literally, made from the remains of dead stars. Those atoms were scattered into space by supernovae, drifted through the cosmos for millions of years, and eventually collected into the cloud of gas and dust that collapsed to form our sun and its planets roughly 4.6 billion years ago. On Earth, over billions of years, those stellar atoms organized themselves into increasingly complex structures, from molecules to cells to organisms to conscious beings capable of looking up at the night sky and understanding where they came from. When you look at the night sky tonight, you might see Betelgeuse in the constellation Orion, that reddish star marking Orion's shoulder. It's a red supergiant, roughly 764 times the sun's radius. A dying star. A star that will explode within the next 100,000 years. And when it does, some of the material it scatters into space might eventually end up in a new star system, on a new planet, perhaps even in new living beings billions of years from now. The largest stars in the universe are engines of creation. Their enormous size, their extreme luminosity, their violent deaths, all of it serves a cosmic purpose. They forge the heavy elements. They scatter those elements across space. They seed new generations of stars and planets. Without them, the universe would contain nothing but hydrogen and helium. No rocky planets, no water, no carbon chemistry, no life. The universe builds big and then breaks it down. Stars swell to sizes that would encompass our entire inner solar system. And then they collapse and explode, recycling their material into new generations of stars and planets, and ultimately life. It's a cycle that has been repeating for over 13 billion years. And somewhere, right now, in some distant nebula, the scattered remains of an ancient red supergiant are collapsing into a new star, beginning the cycle all over again. Somewhere else, a massive star that has been burning hydrogen for millions of years is right now exhausting the last of its core fuel. Its core is about to contract. Shell burning is about to ignite. And over the next few 100,000 years, it will swell into a new red supergiant, possibly becoming one of the largest stars in the galaxy. briefly occupying that narrow range of conditions where physics allows a star to fill a volume the size of a planetary orbit. And think about what this means for the future. Our telescopes are getting better every year. The James Webb Space Telescope is observing the universe in infrared wavelengths, which is precisely the part of the spectrum where red supergiants shine most brightly. Future interferometric instruments may allow us to resolve the surfaces of red supergiants in distant star clusters, seeing their convective cells, their pulsations, their mass loss in real time. We might discover stars even larger than Stephenson 2-18, stars pushing right up against the theoretical maximum of 2,500 solar radii or beyond. Or we might confirm that the current champions are indeed near the ceiling of what physics permits, validating our models of stellar structure and evolution. We're also learning more about how these stars die. Advanced neutrino detectors, like the ones operating in Japan and Antarctica, may someday capture the burst of neutrinos that precedes a nearby supernova by hours. Gravitational wave observatories might detect the asymmetric collapse of a stellar core. If Betelgeuse explodes within our lifetimes, and the chances are admittedly small given the 100,000-year timescale, we would witness the death of a red supergiant with a suite of instruments that previous generations couldn't have dreamed of. We would see it in visible light, in radio waves, in X-rays, in neutrinos, and possibly in gravitational waves. It would be the most thoroughly observed astronomical event in human history. Every generation of astronomers has pushed our understanding of stellar scale a little further. A century ago, we didn't even know that galaxies existed beyond the Milky Way. 50 years ago, our estimates of stellar sizes were crude compared to what we have today. 20 years from now, we may look back at our current measurements and marvel at how imprecise they were. The story of the largest stars is still being written. New chapters are added with every observation, every refined measurement, every improved model. But even as our knowledge improves, the fundamental story will remain the same. Stars are born from gas and dust. They burn through their fuel. The most massive among them swell to extraordinary sizes as they approach the end of their lives. And then they explode, returning the enriched material to the cosmos. This cycle of birth, expansion, death, and renewal is woven into the very fabric of the universe. It's what makes the cosmos dynamic, evolving, and ultimately capable of producing the complexity that leads to life and consciousness. And somewhere else, a red supergiant that has been bloating for hundreds of thousands of years has just run out of silicon in its core. Iron is accumulating. In a matter of hours or days, the iron core will reach its critical mass. It will collapse, and the star, once one of the largest objects in the galaxy, will explode in a supernova visible across millions of light years. These events are happening constantly, across the Milky Way and across every galaxy in the universe. Stars are being born, swelling, dying, and exploding at every moment. It is one of the fundamental rhythms of the cosmos, as constant and as reliable as the tides. It has been going on since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last reserves of hydrogen are exhausted, and no new stars can form. The largest stars are the most dramatic participants in this cycle. They live the shortest lives, but make the biggest impact. They forge the heaviest elements. They produce the most spectacular explosions. They create the densest remnants, and they generate the raw material from which future stars, planets, and perhaps life will be built. When you think about the scale of the largest star ever discovered, 2,150 times the Sun's radius, a star that would engulf everything from Mercury to Saturn, remember that this enormous, almost incomprehensible object is temporary. It exists for a cosmic eye blink, and then it becomes something else, something far smaller but equally remarkable, a neutron star or a black hole, surrounded by an expanding cloud of gas, enriched with the building blocks of worlds. The largest stars are not just large, they are essential. They are the forgers of the cosmos, and their story, from birth through spectacular expansion to violent death, is the story of how the universe became complex enough to produce beings like us who can look up at the night sky and wonder at it all. So, the next time you hear about a star with a radius of 2,000 times the Sun's, a star so large it would swallow Saturn if placed at the center of our solar system, remember that you owe your existence to stars like that. They may be enormous beyond comprehension. They may be dying. They may be unstable and temporary. But they are also the most important stars in the universe for creatures like us. Because without them, we simply wouldn't be here. Thank you for joining me on this journey through the extremes of stellar scale. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, when you look at the stars tonight, you're not just seeing points of light. You're seeing suns. Some of them are modest, like our own. Some of them are enormous beyond comprehension. And all of them, every single one, is part of the story that led to you being here, on this small planet, under this vast sky, capable of understanding it all. Good night, and may you never look at the stars the same way again.